Hi, this is a presentation on some of the elements of our project plan for a brand new middle-of-the-market passenger airliner that we're calling Rambling Wreck 101, RW101. The RW101 is designed to satisfy a very particular need, and this need can be shown by this diagram. As you can see, the middle-of-the-market region is colored by purple. It is between the traditional wide-body and the narrow-body aircraft, with range and capacity between the two. The first question you might want to ask is, why such a need exists? And this comparison might help to answer that question. On the left side, we have narrow-body aircraft such as the A330, B737, and wide-body aircraft such as the A380 and Boeing 747. Compared to the Rambling Wreck 101, our airplane would, in theory, have higher passenger capacity, meaning higher revenue, as well as longer range compared to the narrow body. And while compared to the wide body, the RW101 would have will be more financially feasible for long flights connecting less popular non-hub cities. And also it will be less likely to operate with empty seats compared to the wide-body airplanes. So additionally, as you might know, there are already middle-of-the-market aircrafts existing today, namely the Boeing 757 and 767. But in about 5 years, they will be more than 30 years old, and they will retire soon, thus creating more need for a new generation of middle-of-the-market aircrafts. And as you can see, the business to explain the business case, we have two diagrams here plotting the range of this new generation of aircraft from the west coast and east coast of the United States. On the left, you can see a 6,000 nautical mile range drawn from Los Angeles, representing the west coast, and on the right, you can see a 6,000 nautical mile range drawn from Atlanta, representing the east coast. As a result, all the green areas are places on Earth that you can reach with this airplane. And our potential customers are then international airlines operating transatlantic as well as trans-Pacific flights, especially budget airlines who fly to destinations with lower demand. The forecasted demand that we estimated is about 2,000 to 4,000 aircraft globally. Potential stakeholders are likely to be one of the three major airlines in the United States, as they will benefit greatly if this aircraft is ever to be developed and built. Our mission then is to create a new generation of aircraft that will allow for profitable trans-Pacific and transatlantic flights, connecting major and secondary cities in parts of Eastern Asia, most of Europe, South America, to anywhere in the continental United States. And at the same time, shorter flights inside the United States, domestic flights, can also utilize the same aircraft as the performance doesn't change with a shorter route. This is an estimated timeline of our development of this aircraft. As you can see, the total time it will take is about 6 years. Total cost $12 to $15 billion. And as comparison, this is on the right. This is the developmental timeline of the Boeing 787. Development and production will be subcontracted to domestic and international partners to further reduce development and developmental cost and time, while final assembly will remain in the U.S. This Gantt chart was used to illustrate the life cycle of the design process and lifespan of the RW101. Like I mentioned earlier, total time to get from design to first flight will take about 6 years. The aircraft should be in service for at least 11 years, and then it will be retired.
All right, I'm going to go ahead and move into the concept of operations discussion. This is going to cover a lot of how the aircraft is going to make money for the stakeholders. And to review, the goal of stakeholders in terms of financial and operating costs perspective is that we want to be about 25 to 30%, we want to generate about 25 to 30% more revenue than a narrow body, and we want to be about 30 to 35% more efficient. Basically, our operating costs are about 30 to 35% lower than a wide body would be. Some high-level system design notes. First of all, we're going to be using twin turbofan engines that are capable of producing about 50,000 pound-force. We're also going to have a maximum capacity of about 240 passengers. That's based on a twin-aisle 232 seating and economy. And as you'll see later, a lot of our seat maps and designs are going to be based on less than a maximum capacity of 240 passengers. That's due to business class and premium economy seats being a little bit bigger, taking up a little bit more room. It's also going to have a maximum range of 6,000 nautical miles, as we've discussed, and its maximum takeoff weight is going to be about 230,000 kilograms. To give you an idea of how big that is, a Boeing 737, for example, it's a narrow body, is about half as much. So it's about 100 to 130,000 kilograms. All right, operating costs per hour. We compared our aircraft, the RW101, to a Boeing 777-200, which is a general kind of middle example of a wide-body aircraft. As you can see, there's this table lists out a bunch of different segments that go into the operating cost per hour. You have labor costs, that is flight attendants, that is the pilot. You have your fuel cost, that's pretty self-explanatory. You have your AC cost to make sure the cabin is nice and pressurized and comfortable. You have your maintenance costs that's distributed per hour, and then you have miscellaneous costs that are associated. One of those costs is insurance. Your total for a 777-200, you're looking at about $11,000 per hour, while our aircraft is at about just under $7,000 per hour, and that does meet our goal of 30% cheaper per hour to operate. Next, we're going to talk about ticket revenues. First of all, we went to kayak.com and searched for flights from Atlanta to London in the area of about April of 2020. It's about 6 months out. And we determined these ticket prices for business class, premium economy, and economy as shown in this table. We also game planned our RW101 to have a seating capacity for business class, premium economy, and economy of about 214 passengers. And we're comparing this to a narrow-body example of a Boeing 737-800. That aircraft is going to have about 166 passengers. As you can see, the price for the RW101 is about $170,000. That means that just from ticket revenues per flight from Atlanta to London one way, we're going to make about $170,000. From the 737 on that same flight, it's only going to make about $133,000 due to less passengers. This is an extra about $40,000 in revenue, which is 29 to 30% more revenue per flight from Atlanta to London. This does meet our stakeholder goal and actually goes quite above it from 25 to 30% extra revenue. Here's a map showing some of the typical flights that this aircraft would undertake and their estimated operating costs. We basically just took the operating cost per block hour of our flight of our airliner, which is about $7,000 an hour, and multiplied it by the average flight time from place to place. You have the Atlanta to London flight that we've already discussed. The total operating cost of that is about $60,000. For example, you also have Los Angeles to Tokyo. That distance is about 5,000 nautical miles, and its estimated operating costs just under $80,000. Also shown is Atlanta to Seattle to show that it can still be profitable on domestic flights. We also have Atlanta to Cairo is right about at the edge of our aircraft's range at 5,800 nautical miles. And we have Atlanta to Sao Paulo, which is one of the biggest cities in South America. All right, the functional analysis. One of the ways that we think we can really innovate and make even more money in this aircraft is by minimizing the aircraft turn time. Turn time is the amount of time that the aircraft spends not in the air. This can include taxiing from gate to gate. This can include time at the gate, time refueling, maintenance, all sorts of stuff when it's not flying, not making money. You can see we have passenger planing, we have unloading cargo and luggage, we have refueling, cleaning the aircraft's interiors, loading new cargo and luggage, passenger boarding, and then taxi to runway and takeoff. An alternative boarding measure that was actually suggested by Boeing for the 757 was to load from the outside in. So your passengers with window seats would board first, followed by middle seats, followed by aisle seats. And we believe, and Boeing believed in their assessment, that implementing this measure could cut the passenger boarding time in half. So shown in our timeline, the passenger boarding segment is about 20 minutes. This allows us to push back from the gate at about the 50-minute mark, or even before. And in a normal aircraft of about this size, like a 777 or a 787, this turn time, the pushback time from the gate, is at the 70-minute or 80-minute or 90-minute mark. So we really believe that cutting down on that 20 minutes of passenger boarding time through the outside-in method and through boarding through two doors at once is really going to help save airlines time. Here's our schematic block diagram. Our aircraft is shown in the middle. We have our fuselage, avionics, emergency subsystems, instrumentation, flight controls are all working together. You can see that there's a lot of lines pointing all over the place. We really do believe that this is going to be an aircraft that's going to take a lot of system design. You have a lot of moving parts and pieces that are connected with each other.
So moving into more of the system architecture of the aircraft as a whole, we constructed an n-squared diagram consisting of 7 interfaces that interacted with each other. Specifically, you can see, for instance, the sensors, they relay data to the flight controls, and the flight controls relay data to the data output interface. This is a pretty straightforward breakdown of how those interact with each other. Then going on, we proceeded to create a work breakdown structure of the overall system, and this was specified to the second tier, where you have tier 0 being the aircraft as a whole. On the left here, you can see we have the vehicle itself and the PVS associated with that, whereas in the right-hand side, you can see the overall work broke down. For the PVS, we have the vehicle broken down into 6 main subcategories of products. And for the work, we had mainly 5 areas that we wanted to focus on. So going even more in-depth into the architecture, we went ahead and we analyzed a few paths going from tier 0 to tier 2, starting with the aircraft as a whole. We specified 3 requirements for each step. For the first step, we gave the aircraft a minimum lifetime, a maximum speed, and a maximum capacity, which we felt was very important for the aircraft to have from the beginning. Going from tier 1 to tier 2, we picked the power plant and the empennage, and we showed 3 requirements that both of those had to meet. And these are associated with minimum operational requirements. For instance, the power plant, we wanted to make sure that we know how many we're having, we want to make sure we know the maximum thrust and the life cycle. And then for the empennage, we wanted to have certain requirements related to its functionality. That'll end the presentation, and hope you enjoyed it.